Hello, we are the VR Hallway Group, and we're seeking to leverage implicit social cues to improve autonomous navigation. Implicit social cues are these things given off by humans naturally that can communicate where they intend to move. When humans pass each other in a shared space, such as a hallway, these cues, such as the gaze and the hip orientation of the human, communicate to other humans where they're intending to move. And as a result, humans are able to avoid conflicts with each other. But when robots pass a human, they don't have the ability to leverage these cues and understand where the human's intending to go. As a result, there's often awkward conflicts or near collisions with robots in these hallways. So the problem is that humans and robots cannot communicate with each other, and our solution is to train a robot to interpret and emulate these social cues given off by humans. So far, we've developed a body tracking in virtual reality system that allows us to track the body of the entire body and gaze of a single person, and we expect to use this to train a neural net and then eventually a robot to emulate these social cues. There are two primary papers that form the foundation for our work and have shown that these implicit social cues are important and valuable as signals of navigational intention, or where someone is intending to move. In the first, Hart et al. Have shown that gaze is understood by humans as a strong signal of navigational intention as compared to other visual cues such as LED lights. In the second, Holman et al. Have shown that gaze is the most effective predictor for navigational intention as compared to position, velocity, and head orientation of people.
So we want to record the interaction of two people walking past each other in a hallway to get a better idea of the implicit social cues being exchanged. We want to be able to track both gaze and body position. So currently we can accurately track body position, but when it comes to gaze, it's hard to do so without directly obstructing vision and thus obstructing the social interaction. So we can also use the Tobii eye tracking and Vicon motion capture system, but the problem with that is it's too expensive and it's really hard to set up. So our solution is to do this project in virtual reality, where we have an HTC Vive VR headset and trackers that the headset has an integrated eye tracker. So for our experiment, we're going to have two people walking past each other in a virtual reality hallway, and we're going to be able to track both body movements and gaze, and we're going to have both participants be able to interact with each other like in real world simulation.
So we need some way to fully track the body using these HTC Vive trackers that are usually meant for video games. So often how these trackers are used is they have, let's say, a wrist tracker and a chest tracker, and that's it. And then they will render an avatar in the video game, but the avatar won't really have a super accurate rendering of where the arm is, because they only really know where the wrist and the chest is, and they'll use inverse kinematics to figure out a possible orientation of the arm. That doesn't really work for us. We need to know an accurate understanding of how the arm and the rest of the body is positioned. So we need some way to take these trackers meant for video games and turn it into an accurate skeletal track that we're then able to input into a neural network. So the skeletal track we want to create relies on knowing the positions of the joints. However, we cannot just simply place these trackers on the joints. This is for a number of reasons. For one, they'll simply slip off because the joint moves. In addition, placing a tracker on a joint won't actually track the position of where the joint is rotating about, rather a position further away. You can imagine someone with a really muscular shoulder, the position of the tracker would be quite a ways away from where the shoulder is actually rotating. And finally, it'd be hard to standardize exactly where on the joint the tracker would go. Again, on the shoulder, you could have a lot of different positions where that tracker could be. So we need some way to standardize this. So what we've done is that we've created a calibration algorithm that will help us determine the relative position of all 8 major joints. So we'll know the joint positions based relatively to either a tracker or another joint. And so these joints are the shoulders, the elbows, the hips, and the knees. And so to do this procedure, we hook up trackers to a person on their chest, their biceps, their wrists, their waist, their thighs, and their shins. And the exact position of these trackers doesn't really matter, just that they're on the body parts. And so then we ask the person to move around, and then we collect the rotation and positional data of all these trackers. And so you can see here how if you move the shoulder around, the tracker on the bicep will move in this sort of sphere, in the sphere relative to the chest tracker. So, and you can see the center of that sphere is going to be the shoulder. So we're able to utilize this to find the position of the shoulder relative to the chest tracker. So how we do this is we can take a bunch of data points from the chest tracker and the bicep tracker, and then we're able to use an inverse transformation to put all the bicep tracker data points into chest tracker coordinate space. And that's all the blue dots here are bicep tracker points in chest tracker coordinate space. And so then we're able to fit a sphere. You can see the red sphere, where the center of that sphere is the position of the shoulder relative to the chest. And so we can do a very similar thing with the elbow, except instead of fitting a sphere, you can see we're fitting a circle, because that's how the shoulder or the elbow moves. And so what we want to find here is the position of the elbow relative to the shoulder. So in order to do this, we first perform a forward transformation on the chest tracker data points with the relative position of the shoulder we just previously found. And so this allows us to not have to do another data collection step. And so then with that data, we're able to perform an inverse transformation on the wrist tracker data points to put them into shoulder space. And so that's all of the orange dots here. And so now we're able to fit a sphere, a circle again, and the center of that circle is the position of the elbow relative to the shoulder. And so similar thing, or the same thing can be done on the lower body as well, with the chest tracker analogous to the waist tracker, the shoulders analogous to the hips, and the elbows analogous to the knees. And so now we know all joints relatively to either a tracker or another joint. And so as long as these trackers stay put on the body, we're able to figure out where the joints are. And so what we're able to do is dynamically calculate during the experiment where these joints are, and that allows us to either construct a skeletal model with bones between joints, or we're able to render an avatar, a human-like avatar over these points, which we will do in the experiment to make it look more realistic.
So once we have body tracking set up, we need to set up the multiplayer system. So we have a server that is set up on a third-party computer that uses a TCP IP connection, and this is separate from the 2 clients. And this server will facilitate the transfer of the joint data and the gaze data. And this allows both players to be rendered in virtual reality and in almost real-time manner. And the server will log all the transmitted data for future use. So here we have a video of someone who has undergone the calibration procedure for one arm using our system. So on the left is what Unity renders, and you can see that there are trackers attached to the chest, the bicep, and wrist. However, there aren't trackers attached to the shoulder and elbow, yet you can still see it's pretty accurately rendered, and this is because of the calibration system. On the right is what player 2 would see, and basically this is the data that has been sent through the server, allowing player 2 to interact with player 1 in a real-time way.
And so using this data collected, we will be able to train a neural network to predict the trajectories of human participants walking down the hallway. We're going to be using an autoencoder, which will help force the neural network to learn the most important features of the data. Regarding the past studies that David mentioned previously, they used gaze as a predictor, and they yielded pretty accurate results, so we believe that ours should be similar or better. We'll also train a behavioral cloning algorithm in which a virtual agent will mimic human social cues and should be able to seamlessly walk down a hallway. In order to test this, we'll place 2 avatars in a virtual environment setting, one being a human participant, the other being the virtual agent, and we should see that their trajectories should be similar to 2 human participants walking past each other in a hallway.
So to recap, the main issue that we're tackling here is trying to improve autonomous navigation within shared spaces between humans and robots. The issue is that humans and robots cannot communicate well in these shared spaces like humans would with each other, and so we want to enable robots to learn these implicit social cues like the gaze and hip orientation given off by humans and interpret those, as well as predict where the human will go to avoid conflict. So our main goal is to have a virtual agent eventually pass a human seamlessly within a virtual hallway. And if that's able to happen, then we expect the real robots to be able to similarly benefit from interpreting these visual cues, and as a result, improve autonomous navigation.
And so currently we have created a system to collect data from body tracking in a multiplayer environment. And then our next steps are going to be to create a neural network and use the data sets collected from 2 participants walking past each other in a hallway to train our behavioral cloning algorithm. And to test the effectiveness of this, we'll compare those results to those of the motion generated by our algorithm to a human participant walking past each other in a hallway. We should see that gaze and hip orientation are the most effective cues in predicting where a person will walk. And by using these, a robot should be able to predict human movement and avoid conflicts, which will help improve social autonomous navigation.
All right. Do we have any questions? Surely someone has a question. Oh man. Y'all showed calibration for the shoulder and the elbow. Do you do anything with the knees?
We have.
We didn't save the graph here. It would be similar.
Okay. Yeah, I mean, you answered most of my questions. I appreciate it. All right, let's thank our speakers again.